Hello. In this segment, we'll be studying Chapter 5, which deals with the introduction to continuous random variables. We'll be studying two continuous random variables in Chapter 5 and continuing on with others in Chapters 6, 7, 8, 9, 10, and 11. Well, so let's make sure that everybody understands what continuous random data is. Continuous random data is data that is measured, not counted. So we do not have the case of 1, 2, 3, 4, which we saw in the last segment. In this case, we're finding the probability that the occurrence is within some interval of numbers, not an exact value. Some examples of continuous random variables, or the data that would be produced for them, would be batting averages. So if you have your batting average, that's a percent of the number of times that you have a successful hit over the number of times up at bat. SAT scores, IQ scores, rainfall. This all follows a continuous distribution. In this particular chapter, we're going to be studying the uniform distribution and the exponential distribution. Well, so first, I'm just going to do a little bit of a review about the continuous random variables. The outcomes are measured, not counted. The probability is equal to the area under a curve. Now remember that our total probability has to be equal to 1. And so the total area under the curve has to be equal to 1. Each actual value has a 0 probability of happening. So we can't find the probability that x is equal to 4 or x is equal to 2, but we can find the probability that x is between 1.5 and 2.5, for example, or between 3 3/4 and 5 7/8 within that interval. All right, so what we're also interested in this case, is the formula for the density curve, which is the function, the curve that we're graphing, that we're finding the area underneath. Well, I'm going to start with the uniform distribution because this is the easiest one to do, and hopefully you'll get all the terminology while we're going through this one, and then you'll be able to learn the others just like that. The uniform distribution deals with data that follows relatively uniformly, meaning that we have a pretty constant rate throughout the interval that we have. Sometimes it's also called the rectangular distribution, and this is one of the few distributions that actually has more than one name, the uniform or the rectangular. I'm going to teach this by doing an example that goes along with the example in Chapter 5. And in Chapter 5, you do have the graphs that go along with this example. A bus comes every 20 minutes. The length of time a person waits for the bus is uniformly distributed from 0 to 20 minutes. That means that the amount of time that people wait for a bus, if it's not on a schedule, it's just every 20 minutes. So maybe it's at 7 past and then about every 20 minutes. When you show up at the bus stop, you have anywhere from 0 to 20 minutes to wait, depending upon where you happen to show up in that cycle. Okay, so now we're going to use the notation for the uniform distribution. The notation is x follows the uniform, and as I said before, this is the only one that is sometimes noted by another variable, r, but not very often. X follows the uniform distribution, and what goes in here is the lowest value and the highest value. So in this case, x would follow the uniform distribution going from 0 to 20. What we're measuring is the length of time a person waits for the bus. So the length of time a person waits for the bus will be from anywhere from 0 to 20 minutes. That's how long somebody will be waiting for the bus. Our graph is going to look like a rectangle, which now, maybe you see why, it's sometimes called the rectangular distribution. On the horizontal axis, we have our number line going from 0 to 20, in this case, and we label it the length in minutes of the wait. That's what we're measuring. What f of x represents is this, the graph of this function right here. Here's f, this graph. F of x is what we would graph to get this line going across right here. Now, remember the total area under the curve has to be equal to 1. All right, we're going to just bring back a little bit of algebra, not too much. But from algebra, you learned that the area of a rectangle was equal to the width times the height. In this case, the total area has to be equal to 1. The width is 20. We have a width of 20. And the height, then, is what we're trying to solve for. Now, we're dealing with an example where the height is constant. It's not changing, so that's an easier one. And if we divide both sides by 20, we get the height is equal to 1/20. So I can mark this value off on the graph. This value right here is at a height of 1/20. In general, we can find the density function, f of x, is equal to 1 divided by b minus a, however wide, meaning 1 divided by the width, b minus a. We don't have to start at 0 and go to 20, just this example does. All right, the first one that I'm going to do is the probability that a randomly chosen person waits from 0 to 2 minutes. So this goes along with the first example that you have in your book right here. Find the probability that a randomly chosen person waits from 0 to 2 minutes. So here's our graph. We're at a height of 1/20. And we're looking for, now remember this is a number line, 0 to 20. We're looking for the area between 0 and 2. So we're looking for this area that I'm going to shade in right here. That's the area we're looking at from 0 to 2. So the probability that x, oh, I guess I shouldn't have written it this way. The probability that 0 is less than x is less than 2, that's a better way to write it, is equal to the width of the shaded region, which is 2 minus 0, that's the width of the shaded region, times the height of the shaded region, times 1/20. And so we would have 2 over 20, which is equal to 0.1. So the probability that x is between 0 and 2 would be 0.1. Let's try the next one. The next one that you have in the book is the probability that a randomly chosen person waits from 4 to 15 minutes. So in this case, we're looking for the probability that x is between 4 and 15. The length in minutes of the wait is what we have here. So we're going to shade in. Now remember, we're on a number line. And so we're going to shade in starting around 4. So we have to think, where would 4 be on this number line? Up to 15. Here's 4. Here's 15. And we're going to shade in that area. The height, remember, is 1/20. So we'll mark that off to complete our graph. All right, so now what we're looking for is the probability that x is between 4 and 15. That's what we're looking for. That's the area under the curve that we're trying to find, the probability that x is between 4 and 15. Well, again, we're going to say, all right, so what's the width here? The width is 15 minus 4, and the height is 1/20. And so we're going to end up with 11 out of 20, or the probability that x is between 4 and 15 would be 11/20. Going right along to the next one that you have. What's the probability that a randomly chosen person waits exactly 15 minutes? That's the same thing as saying, what's the probability that the wait is from 15 to 15? Now remember, we could do 14.5 to 15.5, rounding to the nearest minute. But this is the probability that x is exactly 15 minutes. So we're looking for the probability that x is exactly 15 minutes, which is the same thing as saying, what's the area of that line? So we're going from 15 to 15. So the width is 0, and the height is 1/20. And 15 minus 15 would be 0 then. 0 times 1/20 is 0. So the probability that x takes on an exact value would just be 0. The next one that you have is find the probability that a randomly chosen person waits more than 12 minutes, knowing that the person waits at most 15 minutes. So an example of this situation, knowing that the person waits at most 15 minutes, is possibly what happened was somebody got to the bus stop, the bus comes every 20 minutes, and another person is there, and the other person said, I already waited 5 minutes. Now you know that the person who's just reached the bus stop is not going to wait up to 20 minutes. That person will wait up to 15 minutes, at most 15, because someone else said, oh, I've already waited 5 minutes. All right, well, let's see how we can work out this. This is a case of conditional probability. Back to chapter 3. So we're looking for the probability that x is greater than 12, knowing that, or given that, that's the symbol from chapter 3, x is at most 15. So find the probability that a randomly chosen person waits more than 12, knowing that the person waits at most 15. Well, if you remember from chapter 3, we're going to deal with reducing the sample space first before we find the probability. So in this case, we have 10 right here, here's 15. And we're saying that the person will not wait more than 15 minutes. So we're going to cross off that part. It can't happen. The person will not wait more than 15 minutes. At most, 15 minutes is the wait. So what's left over now has to have an area of 1. Well, it used to be that the height was 1/20, because 1/20 times 20 is equal to 1. But now we see, no, this doesn't make sense. It can't be that the height is 1/20, because we're only going from 0 to 15. It's almost as if you started out again and you said, oh, x is uniform from 0 to 15. It's just, we could interpret it that way. So now we know that the height will be 1 out of 15, not 1 out of 20. Now the probability x is greater than 12. Here's 12. By the way, do you notice that I'm not shading in all the way up to 20? We can only go, even though it says more than 12, we have to stop at 15 because we have at most 15. So more than 12, but at most 15. So again, we're going to have the width. The width is going from 12 to 15, so we have 15 minus 12, times the height. And the height is equal to 1/15. So the probability would be equal to 3 out of 15, or 1 out of 5, or 20%, 0.20. So in this case where it was given or knowing, for the conditional, we reduced our sample space. It changed our height. All right, we're going to do one more, and that's to find a percentile. Let's say we want to find the 90th percentile for the time a person waits. Okay, so we're going to be looking at this, and we're looking for the 90th percentile. Another way to interpret that is 90% of the people wait up to what time? All right, so we'll have our graph right here, and we're going from 0 to 20. We want to find the 90th percentile for the amount of time a person waits, and we're going from 0 to 20 right here. And we're going to start shading in and stop when we hit 90%. So this area is equal to 90%. I don't know what this is. We can just call it any letter we want. Let's say K, doesn't matter. And now we know that the probability that x is less than K is equal to 0.90. We're shading in 90% of the area. So we're shading in 90% of the area. And this is equal to K minus 0 times 1/20, which is 0.90. And now we just need to use simple algebra to solve for k. We're going to multiply both sides by 20. And so we have k minus 0 equals 18. And now we add 0 to both sides. Well, this is a simple case because we're starting at 0. But we won't always be starting at 0. So we add 0 to both sides and we get k is equal to 18. So this tells us that the 90th percentile is equal to 18, or 90% of the people wait at most 18 minutes. To find the average and the standard deviation, the formulas are in the textbook, and you can use those formulas for doing that. The second distribution that we're going to be doing right now is called the exponential distribution. And you would have seen this before in some other classes. So let's say, for example, that you took a chemistry class, whether you took this in high school or you took it in college. At some point, you probably studied radioactive substances, and they have what's called a half-life, which means after a certain amount of time, half of the material has decayed and you have half left. And then after the same amount of time, you have half left again. After the same amount of time, you have half left again. That follows what's called the exponential distribution, where we're decaying exponentially. You also could have had exponential growth, which is when you increase exponentially. For example, if you had money that was compounded continuously, and you study that formula, you know that it involved e to the x continuously compounding, and that involved exponential growth. Well, the exponential distribution involves things that decay or decline, and it's how a quantity decays or declines. It's used often in the fields of reliability and in waiting times, and we're going to be studying it here. You might be interested in the length of time, the life of a light bulb, for example, or the length of a long-distance business phone call. Those have been graphed, those lengths, and tended to follow an exponential distribution. Now, how we know that something follows an exponential is that not that we just say, okay, let's say this follows an exponential distribution. How we know that something follows an exponential distribution is usually based upon having graphed the histogram for this. So data was collected, data would be collected, and we would have a graph that would be done. And once we have that graph, we'd say, gee, it looks like it's following the shape of an exponential distribution. And then some tests would be done and performed on the data. One of the tests we'll get to in Chapter 11, which is the chi-square goodness of fit, to see does indeed the data follow what we would expect. The graph of the exponential distribution looks like this. It's decaying or declining. It's curved. It is not a straight line. And in fact, the function that's being graphed is this function right over here. F of x equals m. M is the decay rate, times e raised to the negative mx power. And this is in your textbook, of course. So m is the decay rate, e is a number raised to the negative mx power, and x is our variable that we're graphing down here. The decay rate is a positive number because the negative is built into the formula. X is positive. There's a relationship between the mean, the standard deviation, and the decay rate for the exponential distribution. And that is, for the exponential, the mean and the standard deviation are the same. To determine this, by the way, you would actually need to involve a subject of math called calculus. And this course does not deal with calculus. So you'll just need to know that this is the case and believe me, or I can show you. If you've taken calculus, you can come to my office and I'll show you. So the mean is equal to the standard deviation, and it's an inverse relationship with the decay rate. It's 1 divided by the decay rate. To find the area to the left of x, we're going to use the formula, which would be 1 minus e to the negative mx. And we're going to use a calculator for this. So I'm going to go through and do an example that we have. First example is, suppose that the amount of time in minutes a postal clerk spends with his or her customer follows an exponential distribution with an average time equal to 4 minutes. And we want to find the probability that the clerk spends less than 4 minutes with a randomly selected customer. Okay, so we have let x equal the amount of time that a postal clerk, I'll cover the solution here, I shouldn't have had that showing, amount of time that a postal clerk spends with his or her customer. The time is known to have an exponential distribution with an average time equal to 4 minutes. Find the probability that the clerk spends less than 4 minutes with a randomly selected customer. Okay, our solution. What we're measuring is the time. X is positive, time is positive. We know that the decay rate, or the average actually, what we know is that the average is equal to 4, which is 1 over the decay rate, so the decay rate is 1/4, or 0.25. If we go to graph this now, we're going to have a graph going down like this. And right at the top here, we have 1/4. That's the decay rate. And we're looking for the probability that x is less than 4. Now, from years of graphing exponential distributions, I can tell you that the average is sort of where, if you think of this as a slide, where the slide starts to level off just a little bit. So this is the average right here. U is equal to 4. And I want to find the area to the left of 4. Now, the exponential distribution is not symmetric. And that tells us that the mean and the median will not necessarily be the same. So we're looking for the probability that x is less than 4. This is equal to 1 minus e raised to the negative 0.25 times 4. I'll just do this one on my calculator with you because you may not be as familiar with the e to the x function. So we have 1 minus, on most calculators, the e to the x function is near the natural log function, and this is no exception. Here's the natural log function. E to the x looks like e with a little x as the exponent. All right, so I press that. E raised to the negative 0.25 times 4. And that's what we'll have. And we get 0.6321. So that shows us on our graph that this area right here is 0.6321. This is the probability that the area is less than, or the x is less than 4. If you notice, the mean is 4, but the mean in this case is the 63rd percentile. It's not the median. All right, if we wanted to find another one, the probability that the clerk spends 3 to 4 minutes with a customer. So now we're looking for, we have our graph again. Now we're looking for the probability that x is between 3 and 4. This is a number line, 0, 4, so 3 would be right here. Okay, so we're looking for the probability that x is between 3 and 4. Well, we know that the total area to the left of 4 is 0.6321. That's all the area to the left of 4. So if we want to find the area between 3 and 4, we need to subtract out this area right in here. Okay, so we need to subtract out that area. And to do that, we will now do this again, and we will have, instead of 4 as x, we'll have 3 as x, and I get 0.5276. So that tells me that this area in between 3 and 4 is 0.6321 minus 0.5276, or 0.1045. So that's the leftover area. Okay, the last part that we're going to do for this segment is to find the median. Now, if you noticed on the graph when you drew it, the area to the left of 4 was 0.63, about 0.63. The area to the left of 3 was 0.5276. So the median is even less than 3. So let's look at this graphically right here. If we look at the graph on this part, here's 4, sort of where the slide starts to even out. Here's 3. The area to the left of 3 is 0.5276. the area to the, but we want the 50th percentile, so we're looking for where half the area is, meaning that this area right here is 0.50. So what you're going to need to do, since this segment is just about over, is to follow the instructions in the book. And you might need to do, sometimes students need to do a bit of a review with the natural logs to figure out how to solve for x, how we're solving for x. But there is a formula for it on the summary page. And so if you don't want to go through the actual taking of the logs of both sides, you could start just with the formula for the summary page. What I do suggest, though, is that you start with drawing a graph the way I did it. I looked at this and I took information from the previous sections. And what I noticed from the previous sections was that the area to the left of 4 was too much for what we wanted. The area to the left of 3 was too much. So I had to come down here. So I would expect my answer to be more than 0, but less than 3. Well, what we've done in this segment is start the continuous distributions with the uniform and the exponential distributions. Work on those problems because we'll be having some more distributions coming along. Uniform distribution tells us that each region seems to have about the same chance of happening if the regions have the same width. The exponential deals with decay over time. And with the next segment, we'll be starting the normal distribution, which is the most widely used distribution there is.